Welcome to AI Paper Slop. So imagine spending, I don't know, 3 agonizing weeks manually tweaking a system prompt, setting up this massive lang chain orchestration for an AI agent.
Oh, I've been there. It is brutal.
Right. You finally get the execution loops working perfectly. Your agent handles files, it catches errors, navigates the terminal flawlessly, and then your company upgrades the underlying LLM to the newest version.
And suddenly everything is just completely broken.
Exactly. It's looping, it's hallucinating file paths, it's overwriting its own code. If you are building or deploying LLM agents right now, you know this exact pain.
It's the biggest bottleneck in agentic AI today.
Yeah, so today we are doing a deep dive into a paper titled Self-Harness, Harnesses that Improve Themselves. This was published by Hangfan Zheng and a team at the Shanghai Artificial Intelligence Laboratory.
It's a really fantastic piece of work.
It is. And here is the core insight right up front. This paper introduces an automated 3-stage loop where an LLM analyzes its own execution logs, isolates its recurring bugs, and then writes actual code to permanently modify its own operating rules.
Yeah, and the results are pretty staggering. They tested this self-improving loop on Terminal Bench 2.0, and it boosted held-out pass rates by up to 60%.
Up to 60%.
Right, across 3 wildly different models, MiniMax, Qwen 3.5, and GLM-5. And the kicker is, no human engineers were required.
0 human intervention. So let's get straight into how this completely eliminates the bottleneck of system scaffolding.
The paradigm shift here is, well, it's profound because it targets the most brittle part of modern AI systems. I mean, we spent the last few years treating the model's neural network weights as the main engine, right?
Yeah.
While human engineers act as the mechanics, just constantly running alongside the car, swapping out the tires and tweaking the steering wheel while it's driving.
Right, trying to guess why an agent got stuck in an infinite loop.
Exactly. But with self-harness, we're moving away from that. The model is diagnosing its own structural flaws and deploying the fix itself.
Okay, so we really need to unpack this bottleneck of human engineering first, because the term harness, it can mean a lot of different things depending on what stack you're working in.
Oh, definitely. It's kind of an overloaded term.
Yeah.
Yeah.
So before we dissect the actual algorithm, let's establish what the authors mean by harness and why manually coding them is failing us as models evolve at this breakneck pace. We are talking about the non-parametric scaffolding, right? The layer mediating the model and the environment.
Yeah. To put it simply, it's all the code wrapping the LLM API call. It is not the billions of parameters or the actual neural network weights. It's the physical workspace.
The environment it lives in.
Right. It includes the system prompts, the available tools, the memory management structures, the verification rules, and the orchestration logic, like, the Python while loops that decide when the agent is allowed to try a field command again.
So if the model is the astronaut, the harness is the spacesuit and the life support system.
That's a great way to put it.
And the scaling problem we face is that different models have entirely distinct behavioral patterns. Like, an OpenAI model might be incredibly cautious about tool use,
Very cautious, yeah.
while some open source model might wildly fire off terminal commands without checking the directory first. So a spacesuit designed for an astronaut on Mars might completely crush an astronaut trying to survive on Venus.
Exactly. A harness that makes one model perform perfectly often just completely paralyzes another.
Which is like trying to force 3 completely different operating systems to use the exact same hardware drivers.
And that's why copy-pasting your orchestration framework from last year onto this year's model leads to such severe regressions. The agent's habits, its error modes, its sensitivities to prompting, they're entirely unique to its architecture.
So a human engineer just can't intuitively predict all these quirks.
They can't. It's impossible.
But wait, the idea of having AI optimize its own behavior isn't entirely new, right? I mean, we've seen projects where an LLM critiques another LLM's output. So how is self-harness fundamentally different from existing optimization methods, specifically things like meta-harness?
That's a really crucial distinction. Methods like meta-harness rely on a stronger external supervisor.
Okay.
You basically hire a senior developer, say a massive model like GPT-4, to look over the shoulder of a junior developer model, analyze its mistakes, and rewrite the junior model's code.
Oh, I see.
Yeah, but self-harness completely internalizes that loop. The agent improves its own operating harness using its own weights. There's no external supervisor.
It's doing it all itself.
Exactly. The authors actually include a fantastic quote from the philosopher Henri Bergson in the paper.
Oh, I love seeing philosophy in technical papers. What's the quote?
He argued that for a conscious being, To exist is to change, and to mature is to go on creating oneself endlessly.
Wow, that frames the engineering perfectly. It's not being supervised from the outside. It is continually creating itself based on its own lived experience in a specific environment.
Perfectly said.
Okay, so let's look under the hood at how this actually works. Because how does the agent fix its own code without accidentally bricking its own operating system?
Yeah, that's the real danger.
Right. So the researchers map this out as a three-stage self-improvement loop. And it starts with stage 1, weakness mining.
This is basically the behavioral evidence gathering phase.
Uh-huh.
The model, with its neural weights strictly frozen, that's important, it runs on a set of held-in training tasks.
Okay.
And this generates execution traces. Think of a trace as a highly granular, step-by-step log of everything the agent did, every batch command it executed, the standard output it got back, every tool it called, and every error it hit.
Just a massive text log of the whole session.
Right. Then, the system takes all the traces that ended in failure and clusters them together. But crucially, it doesn't cluster them by the surface-level symptom. It clusters them into verifier-grounded failure signatures.
And that distinction is incredibly important. It separates the symptom from the underlying disease, right?
Yes.
Because a surface symptom is just, say, a timeout. The verifier just says, failed, execution took longer than 900 seconds.
Which tells you nothing about why it failed.
Exactly. But the root mechanism, the actual disease, might be that the agent got obsessed with reading the exact same log file over and over because it didn't know how to parse a specific string.
Right. If two separate runs fail because of a timeout, a human might just tell the agent, hey, work faster.
Which is useless.
Completely useless. But the weakness mining stage traces the terminal failure back to the abstract agent mechanism that actually caused it. So this gives the system highly actionable, recurring bugs to fix, rather than just a pile of confusing, isolated mistakes.
Which naturally flows into stage 2, harness proposal. So once you have this cluster of root cause failures, how do you actually trust the model to write the fix?
Well, the model itself acts as the proposer. It takes those failure signatures and generates multiple, diverse, minimal modifications targeting the specific failures.
Okay.
And these edits are applied to editable surfaces, like tweaking a runtime policy or adding a highly specific verification instruction to the system prompt.
And the operative word there is minimal, I assume?
Oh, absolutely. The prompt given to the proposer strictly restricts it from completely rewriting the entire control architecture.
Wow.
We don't want the model throwing out the baby with the bathwater.
Right, right.
It has to target a specific failure mechanism with a narrow, bounded edit to the execution protocol.
Okay, here is where I have to push back a little bit.
Go for it.
I can easily see a model analyzing its failure, proposing a quote-unquote fix for one specific bug, and then accidentally destroying its ability to handle everything
An
else.
overfitting.
Classic overfitting, yeah. It hard codes a solution to pass one specific test case, but basically lobotomizes its general reasoning. So how conservative is the validation gate in stage 3?
That is the primary threat to any automated code generation, which is why stage 3, proposal validation, acts as a brutal, unforgiving filter.
How brutal are we talking?
The candidate edits undergo rigorous regression testing on both held-in splits and held-out splits of the data. An edit is only accepted into the harness if it improves at least one split without degrading the other in any way whatsoever.
Wait, let me make sure I have the math right on this. If an edit boosts the held-in pass rate by, say, 20%, but drops the held-out pass rate by even 0.5%, it gets tossed out.
Instantly rejected. It's gone.
Wow.
Yeah, the acceptance rule is defined mathematically. The change in the held-in pass rate must be greater than or equal to 0. The change in the held-out pass rate must be greater than or equal to 0. And the maximum of those two changes must be strictly greater than 0.
So no step backward is allowed.
None. And remember, the model's underlying weights and the evaluator remain totally fixed during this whole process.
Sure, mathematical validation sounds great on paper, but in the wild, testing environments have massive blind spots. If your held-out data doesn't happen to capture a weird edge case, couldn't the agent still hard-code a terrible habit?
Like what?
Like, it learns a shortcut that passes the benchmark perfectly, but would catastrophically fail in a real production server.
I mean, that is the fundamental limitation of any benchmark-driven optimization, absolutely. If the benchmark lacks diversity, the validation gate can't protect against the blind spots.
Right.
But within the scope of this system, this regression test ensures the agent is discovering broadly useful workflow rules. It forces the model to find generalized solutions like always check if a file exists before modifying it, rather than just memorizing a specific file path to pass a failed task.
That makes a lot of sense. The environment has to be punishingly diverse. Which brings us to the experimental setup. To prove this strict validation loop actually produces smarter behavior, the researchers needed a realistic, highly controlled testing ground.
They did.
And they needed a truly minimal starting point to prove the model was doing the heavy lifting, not the humans. So let's talk about the setup. They utilized Terminal Bench 2.0.
Yeah, so Terminal Bench 2.0 is designed to test an agent's ability to interact with realistic, complex terminal environments. But to ensure they were measuring the actual harness performance and not just random external noise, they containerized everything.
Okay, in a harbor environment, right?
Exactly, on a massive, isolated 64-core machine.
I noticed they even capped the outbound network bandwidth to 2 megabytes per second, which seems like an odd detail until you think about it.
That was brilliant.
Yeah, they wanted to completely prevent latency variations from causing random timeouts and muddying the data.
Yeah.
Pure isolation.
Pure isolation. And they focused on a 64K subset, specifically excluding multimodal tasks or highly unstable web interactions.
Because the live web constantly changes, which destroys reproducibility.
Exactly. So they have this pristine, isolated terminal. And the initial harness they started with was built on the Deep Agent SDK, but they stripped it down to its barest essentials.
Like a blank slate.
An absolute blank slate. Just a basic benchmark-facing system prompt and default shell and file system tools. Nothing fancy, no complex human-engineered orchestrations that you usually see in state-of-the-art LangChain setups.
So the researchers essentially dumped these highly advanced LLMs into a raw, dark terminal with nothing but a Swiss Army knife and a blank sticky note.
Pretty much.
And just told them to iteratively write their own comprehensive employee handbook.
That is exactly what happened. And they tested this on 3 entirely different architectures to prove it wasn't a fluke. They used MiniMax M2.5, Qwen 3.5, 35B, A3B, and GLM5.
Okay, so the results are where this paper goes from an interesting theory to a massive practical breakthrough. Because the quantitative leaps are undeniably huge, but the qualitative changes what the models actually chose to write in their own handbooks are completely different from each other.
It's wild to look at.
Let's hit the overall numbers first. On the held-out pass rates, meaning tasks the models never saw during their self-improvement loop, purely generalized capability. MiniMax M2.5 jumped from 40.5% to 61.9%.
Huge jump.
Qwen 3.5 went from 23.8% to 38.1%, and GLM5 went from 42.9% to 57.1%.
Those are massive relative gains for doing absolutely nothing to the model weights. It exposes how much raw capability is left on the table by suboptimal, human-written scaffolding.
We blame the model for being stupid when really we just gave it a terrible workspace.
Exactly. So let's look at the model-specific edits, because this is the real revelation here. Take MiniMax M2.5.
Okay.
Its primary weakness during the mining stage was getting stuck in stalled tool loops. It would just endlessly call tools without making any actual progress.
If MiniMax is stalling out in tool loops, the human instinct is to just write a master prompt in all caps saying, "Do not get stuck in loops."
It never works.
Right. So what did the model actually write into its own policy to fix this?
It got highly mechanical. It edited its own runtime control policy to force a hard redirection after exactly 50 tool calls.
Oh, wow.
Yeah, it literally wrote a conditional instruction saying, "You appear to be stuck in a tool loop. Stop repeating the same failed path."
That's so concrete.
Furthermore, it updated its instructions to use correct content tags for structured outputs. And crucially, to create required output artifacts early in the process rather than waiting until the very final step.
That is fascinating. MiniMax realized it was the kind of worker who stares at a blank screen procrastinating, so it forced itself to write the first draft immediately.
That's a perfect analogy. Now contrast that with Qwen 3.5. Qwen had totally different neuroses.
Okay, what was Qwen doing?
It struggled heavily with file overwrites and executing exact command retries. When a tool failed, it would aggressively try the exact same broken command over and over again.
So it's the neurotic worker who tries the same broken key in a lock 100 times, expecting a different result.
Exactly. And its self-generated fixes reflect that exact pathology. Qwen didn't write a rule about 50 tool calls. It added a dependency pre-check instruction, basically telling itself to always verify that the right modules are installed before proceeding.
Smart.
It added a strict loop breaker, forcing it to create missing artifacts within 2 steps of noticing they were missing. And most impressively, it designed a strict tool error middleware guard.
Wait, a middleware guard. For anyone listening who builds APIs, middleware acts as a layer that intercepts requests before they hit the core logic.
Right.
Explain how an LLM writes its own interceptor in this context.
So the agent injects a piece of logic into the runtime that triggers specifically when a tool error occurs due to missing file. Instead of just passing the raw error back to the LLM and hoping it figures it out, the middleware intercepts the error and feeds a critical high-priority prompt back to the agent.
What does the prompt say?
It says, "Do not continue exploring. You must locate the missing artifact and create it immediately."
It built a panic button.
It built a panic button that overrides its own core logic.
That is incredible engineering. And then we have GLM-5, which had a totally different problem, right?
Yeah, GLM-5 kept forgetting its environment setups.
What do you mean?
Well, it would brilliantly install a package or change a path variable and then try to run a command in a new shell session, only to fail because the path modification didn't persist.
Oh, it's the genius worker who keeps forgetting where they parked their car.
Exactly. Shell environments are ephemeral. A human engineer knows that, but a language model often forgets.
So how did it fix it?
GLM-5 added explicit instructions to its harness to ensure that modifications to the path persist globally across shell sessions, using things like Bash-Shock or profile scripts.
Oh, that's clever.
Yeah. It also added a verification instruction to break itself out of analysis paralysis. It literally told itself, if you have been exploring without producing artifacts, transition immediately to implementing and testing.
This completely destroys the idea that there is a one-size-fits-all master prompt. We are way past the era of copy-pasting a generic, "you are a helpful and meticulous coding assistant" prompt.
How about it's dead?
Yeah. Qwen 3.5 built an aggressive micromanager to handle file dependencies and intercept errors, while GLM-5 just needed a sticky note reminding it to save its work globally across shell sessions.
Because the agent knows its own failure modes better than we do. A human engineer observing Qwen might try to write a slightly better general prompt, but they likely wouldn't design a highly specific tool-triggered middleware just to stop the agent from stubbornly retrying exact commands.
So let's look closely at the actual execution traces to see exactly how these harness edits alter the agent's behavior mid-task, because the paper provides some incredible trace-level case studies that show failures transforming into successes.
Yeah, the traces are really eye-opening.
Let's start with the MiniMax case on a task called Count Dataset Tokens. Paint a picture of what happened under the initial blank slate harness.
Okay, so under the initial harness, MiniMax is instructed to count the tokens in a specific dataset. You look at the log, and it successfully finds the dataset metadata. Great.
Okay, so far so good.
But then it just keeps exploring. It checks different configurations. It reads readme files. It previews data samples. It does this endlessly, generating massive amounts of logs until it hits the hard 900-second timeout.
Wow.
Yeah, it never actually creates the required answer.txt file. The verifier fails it because the output is just missing.
It got totally distracted by its own curiosity.
Exactly.
But post-harness edit, after it applied its self-generated rule to create output early, what does the terminal log look like then?
It's a remarkably clean workflow. It finds the metadata, identifies the target subset, and immediately computes the token count. Then it creates the answer.txt file, writes the number, and this is the critical part, reads the file back to verify the content before stopping.
Oh, it double-checks its work.
It goes from a 900-second meandering failure to a precise, successful execution in a fraction of the steps.
Now let's look at the Qwen 3.5 trace on the extract elf task. This trace is wild. What goes wrong initially?
So the agent is tasked with parsing an ELF binary file and extracting specific memory values into a JSON file. Initially, it successfully writes a JavaScript extractor script.
Okay.
But when it runs the script, it hits an error regarding large integer precision. So it tries to fix the script, it gets an overwrite error, it tries again. The trace just shows this frustrating rapid-fire loop of exact command retries, hitting the same overwrite errors over and over.
It's just spinning its wheels.
Right. The agent essentially gets flustered, and right before the run ends, it executes a remove command and deletes the script entirely.
Wait, it rage quit. It literally deleted the file it was supposed to be working on.
It absolutely did. It just warmed its own work, and obviously the verifier fails it because the necessary file doesn't exist.
That is hilarious and tragic.
But after Qwen applies its self-generated harness update, that tool error middleware interceptor, we talked about the sequence changes entirely.
I'm looking at the updated trace here, and it looks like it hits the exact same integer precision error early on. But it doesn't spiral this time.
Exactly. It hits the error, but the middleware intercepts it. It injects that critical system prompt we mentioned. It physically stops the agent from continuing its ineffective retry loop.
Wow.
The prompt forces it to pause and recreate the missing script immediately. The agent complies, rewrites the extractor to handle the integer correctly, validates the JSON output, and leaves the required artifact present for the verifier to pass.
It's fascinating because the fix isn't magically making the LLM's neural network smarter. It's not learning new JavaScript syntax in its weights. It's building better guardrails.
That's the perfect way to look at it.
It's like adding a syntax highlighter and an aggressive auto-linter to your IDE. The linter doesn't teach you how to be a better software architect, but it physically stops you from deploying code with a missing semicolon.
The performance boost stems entirely from targeted workflow changes grounded in real behavioral evidence. When you just pile instructions into a master prompt, models suffer from lost-in-the-middle effects.
Right, they forget the instructions by step 10.
Exactly. But by injecting logic into runtime policies or middleware, the harness intercepts the model exactly at the moment it's about to stumble. It proves that a self-diagnosed, highly tailored scaffold is vastly superior to generic prompt bloat.
So what does this all mean for the daily reality of agent deployment? To summarize everything we've covered, the self-harness paradigm proves that LLMs can autonomously design, validate, and optimize their own operational rules.
Yes.
They read their own traces, isolate their unique flaws, propose minimal code fixes, validate those fixes against strict mathematical non-regression tests, and evolve into highly capable systems.
And it scales precisely because it requires zero human intuition.
Right.
As we get new open source models dropping every few weeks, each with their own bizarre quirks and attention mechanisms, engineers won't need to spend weeks manually tuning their LangChain logic.
You just drop the raw model into the self-harness loop.
Yeah, give it a baseline environment and let it read its own failures until it builds a scaffold that perfectly maps to its specific neuroarchitecture.
I want to leave you with a final, provocative thought to chew on. Right now, as impressive as this is, self-harness works within bounded, pre-declared surfaces of a benchmark setup.
True.
The model is allowed to edit specific instruction fields or toggle predefined runtime policies in a controlled Harbor container. But what happens when we move beyond benchmarks?
Oh, that's where it gets crazy.
Right. What happens when we give an agent the ability to invent entirely new, undeclared tool architectures in the wild? If a model is continuously rewriting its own underlying source code, altering its memory management, and inventing its own API integrations as its real-world environment changes.
Where does the harness end and the model begin?
Exactly. At what point does the harness end and the model begin? Thanks for joining us for this deep dive into the source material. We'll see you next time on AI Paper Slop. Keep questioning the scaffolding.